All right, okay. So again, we'll continue with our study of Schrodinger bridges and entropy regularized optimal transport. I will put a set of homework problems on this. But how are you guys feeling after the last lecture? Did you guys understand the basic problem and the concepts that were taught? Do you have any questions that I can answer now before I move on with them? Anybody? All right, okay, then. So this was a problem that we were talking about. So recall the setup. So I have two probability measures, mu and nu. So mu and nu are two probability measures. So these are elements in P2 of RD. And I'm looking into the following problem. I'm looking into what is called the EOT, epsilon, mu, and nu. And this is a problem that is trying to solve the infimum over all couplings of mu and nu. The first term is exactly the same as your regular optimal transport. And the second term is a penalization of entropy. Okay? This is a strictly convex optimization problem on a convex set. The unique minimizer is called the Schrodinger bridge. At temperature epsilon. Between mu and nu. Now, this topic of entropy regularization and Schrodinger bridge is typically not covered in the standard optimal transport textbooks, mostly because it's new and it's more statistical. But now there are some excellent resources here. So you can look into this textbook on statistical optimal transport by Chewy, Nansweed, and Rigole. There are also some online notes by Nutz, which also gives a good introduction to this subject. So the textbook is more about statistical theory of optimal transport. I encourage you to all to check it out because it does much more than just entropy regularized optimal transport. It really talks how to do statistics with optimal transport. The online note says, does the bridge vary continuously with epsilon? That's a great question. Yes, it does, but it's not actually obvious that it does. But yes, it does. Actually, what happens to its continuity with epsilon and epsilon gets close to zero is actually a problem of current research. We don't fully understand it. But even this simple question that whether the bridge varies continuously with epsilon is actually not very well understood. We actually don't understand how much does it vary with epsilon. So that's an excellent question. So you have a research problem here. Good. Any other questions? Okay. So we'll talk, maybe not this either today or tomorrow. We'll talk about why statisticians and people who do applications of optimal transport prefer this version. But we already mentioned this last time in class. The reason why people prefer this version is that this can be efficiently computed. One of the reasons people like this regularization is that this can be effectively computed, because this can be computed efficiently due to what is called synchron algorithm, or the IPFP. Second. Oh no. Okay, how do I delete this? How do I get rid of this? Or synchron, or the IPFP algorithm. So this is for discrete data. This is for continuum data algorithms. This is a big part of our current research. So we'll go over what this algorithm is, what it does, and so on, because it's just so important both in applications and also mathematical theory. So actually, rest of the week, we'll actually talk more and more about synchron algorithm. So let's see where this comes from. And part of the reason I've already explained last time. So let's start with the IPFP. So why is this important? It is important. It comes from so by the way, both synchron and IPFP, by the way, are much older than statistical optimal transport. These algorithms have been existing since 1950s and 60s, because these have many other uses. So why it is important is because we know something about how the Schrodinger bridge looks like. So this is a theorem we talked about last time by Ruschendorf. That the Schrodinger bridge, which something happened here. Okay, the Schrodinger bridge, epsilon, you knew, which is the arg-inf over the set of couplings. Norm squared d gamma plus epsilon entropy of gamma. This admits a density, admits a joint density. And if I call this, let's say, this joint density by gamma epsilon star xy, then it looks like the following. Gamma epsilon star xy divided by mu x, mu y, which are also densities by just my general assumption. This is of the form e to the power minus 1 over 2 epsilon norm of y minus x squared. And then minus a epsilon of x over epsilon minus b epsilon of y over epsilon. This admits a joint density. These a epsilons and b epsilons, the theorem says there will exist potentials a epsilon and b epsilon such that the resulting gamma epsilon star is a coupling. And once you have that, it must be the Schrodinger bridge. And this must be the Schrodinger bridge. Okay. So again, what is the theorem saying? The theorem is saying that given these two marginals mu and nu, there will exist some a epsilon and b epsilon, some two functions, such that a density of this form, e to the power minus 1 over 2 epsilon norm of y minus x squared minus a epsilon over epsilon minus b epsilon over epsilon, will satisfy the marginal constraints mu and nu. When it does, this is automatically the Schrodinger bridge, which means that this is the argin of this optimization problem. And moreover, there will exist something. So there's a unique one because it's a unique minimizer. So last time we argued that why, if it does exist, one of these a epsilon, b epsilon, this must be the Schrodinger bridge. Last time we argued we gave an idea of the proof of why, if a epsilon, b epsilon exists, gamma epsilon star must be the Schrodinger bridge. And this idea was due to the fact that what we used is scale projections. This is a very important idea, again, appears in many, many other contexts. This is an idea that when you're doing a Kullback-Leibler projection of one probability measure on a certain set of probability measures, then if that certain set of probability measures is given by linear constraints, then this Kullback-Leibler projection must take a particular form. It's e to the power a constant time that constraint, and this is just an idea of Lagrange multipliers. And the fact that pi is basically given by a set of linear constraints, a countable collection of linear constraints, tells us that that if you have a function of this type a epsilon with these potentials a epsilon and b epsilon, this must be the KL projection. What does not follow from the proof that you can actually find such an a epsilon and b epsilon. Okay, that is not immediate, that you can actually, there will exist some potentials a epsilon and b epsilon, such that the gamma epsilon star is in this set pi of couplings. And we're going to present a proof today, which is originally due to the French mathematician Forte, which actually uses IPFP. Although it wasn't realized for a long time, it only got rediscovered much more recently, that this was actually using Synchron or IPFP to show this. So let's see this. Let's see this other proof. So proof of the existence of a epsilon b epsilon can be argued using IPFP or Synchron, and this argument is due to Forte. So where do we start from? We start from the fact that what are called Schrodinger's equations, that these, if gamma epsilon star has to be in the set of couplings, these functions a epsilon and b epsilon must satisfy some constraint. So this is the Schrodinger system of equation. So we have that gamma epsilon star xy, it's here. This is the density. And then I would get that this, when integrated with respect to dy, I would get mu x. And gamma epsilon star xy integrated with respect to x would give me nu y. These are the two systems, that are the two marginal constraints that I get. If I write them down in terms of this expansion that is given here, and I integrate this, then I would get implies is two equations. One is a epsilon of x is equal to epsilon log integral e to the power minus 1 over twice epsilon norm of y minus x norm square minus b epsilon of y over epsilon nu y dy. B epsilon of y, the same thing, epsilon log integral e to the power minus 1 over twice epsilon x minus y norm square minus a epsilon of x over epsilon nu x dx. Okay, that's what I get from this, the marginal constraint, by simply integrating and taking terms out. Now, one thing I should say here is that I am not quite keeping track of this term, the constant term here, but if you wish, you can actually write this guy as 2 pi epsilon to the power d over 2 as well. It doesn't matter. This is just a constant. You can try to get it inside those b epsilons, a epsilons, or you can multiply it here. This is unimportant. You can do anything that you want. But one convenient way of seeing this is that the first term that you're integrating, which is e to the power minus 1 over 2 epsilon y norm of y minus x norm square, this is a Markov operator corresponding to Brownian motion. So consider the Markov operator corresponding to Brownian motion. So what do I mean by this? This is very simple to Brownian motion. So this is very simple. So imagine that you have Brownian motion. So BT, this is my standard Brownian motion in RD. And I can define my R epsilon of any function psi of, let's say, x to be the expected value of the function psi applied to b at time epsilon, given that b0 is equal to x. So if I write it in terms of the transition kernel, I would get that this is equal to psi of y 1 over square root 2 pi epsilon d over 2 e to the power minus y minus x norm square over twice epsilon dy. Do you get what I'm saying? The reason why I'm writing this is that I think of this R epsilon as an operator over functions. I have a function psi. I apply R epsilon on my function psi to get another function, R epsilon psi, that I can now evaluate. This is a Markov operator for Brownian motion. If you've done some stochastic calculus, you will know that this is a fundamental operator when you do stochastic calculus. In terms of these Markov operators, you can see that A epsilon of x may be written as epsilon log, so R epsilon of e to the power minus b epsilon over epsilon nu. This applied to x. And similarly, I can write b epsilon of y as epsilon log R epsilon e to the power minus a epsilon over epsilon mu at y. Do you see what I'm doing here? Are you Are you guys following what I'm written there? I'm just doing algebra here. Nothing so far has been done. Essentially writing down the marginal constraints explicitly and just replacing these integrals by this integral operator notation so that it just becomes convenient for me. That's it. You follow this?
Yep. Pretty
Okay, good.
straightforward. Yeah.
One of the properties that you see, and this is a property that we're going to use here, that because this is a Markov operator, R epsilon, it has a property that if psi is non-negative, then R epsilon of psi must also be non-negative, right? Because I'm taking an expectation. All expectations operators have this property. If the function is non-negative, then expectation of the function is non-negative. So this is clearly true. In fact, a stronger statement can be said that if psi1 is greater than or equal to psi2, then R epsilon of psi1 must be greater than or equal to R epsilon of psi2. Again, same thing. Expectations is a linear operator. Expectation is a monotone operator. So if I have two functions, one larger than the other, the expectation of the larger function must be necessarily bigger than the expectation of the smaller function. Obvious properties, but we'll use this later. Now from here, I can write that A epsilon of x is equal to epsilon log R epsilon. Now, e to the power minus b epsilon. Look at what's happening here. E to the power minus b epsilon. So e to the power minus b epsilon, if I rewrite this, I get e to the power minus b epsilon over epsilon. This is equal to, so b epsilon over epsilon is log of r epsilon. So negative of this is negative of log. So e to the power is e to the power negative of that. So that's a reciprocal. So I get this is 1 over r epsilon e to the power minus a epsilon over epsilon mu. And so if I substitute this back here, I get this is epsilon log r epsilon. And then I substitute this back here. What I get, this is nu divided by r epsilon e to the power minus a epsilon over epsilon times mu. And so what I get from here is that a epsilon must be a solution of this fixed point problem. So a epsilon must be a solution to this fixed point problem. And this is what both synchron and IPFP equation is based on. I'll do a slight change of notation to conform to exactly what synchron does. So I'm going to change the potentials. So change the notations to.
We haven't given any properties for, like, we don't have any smoothness assumptions or well-behaved assumptions on A epsilon X, do we?
Nope,
It's just anything.
In fact, the way that the proofs go of proving smoothness is exactly by saying A epsilon has to satisfy this fixed point equation, and therefore it must satisfy certain smoothness. As you can see from here, on the right-hand side, I have an integral operator R epsilon acting on e to the power minus A epsilon. So it gives some additional smoothness. Then I have another R epsilon adding, so that gives another additional smoothness. And therefore, A epsilon must be smooth. And so this is how typically the proofs will go. If it has to be a solution of the six-point equation, it must be smooth.
Okay.
But no. So I'm going to change slightly my notation, and this is just to conform to what the algorithms actually do. So I wrote that gamma epsilon star xy is mu x, nu y, e to the power minus norm of x minus y norm squared over 2 epsilon, e to the power minus a epsilon of x over epsilon, e to the power minus b epsilon of y over epsilon. Call this to be phi of x, phi epsilon of x. Call this to be psi epsilon of y, the whole thing. So this is non-negative, and this is non-negative. Sorry, not double, but just greater than or equal to. And this is non-negative. And in that case, I can write from here that in terms of phi epsilon of x, what I get is that phi epsilon of x phi epsilon of x, which is e to the power minus a epsilon of this, would be equal to 1 over r epsilon nu divided by r epsilon phi epsilon mu. Okay, and that is what I'm going to write it as a function capital phi of small phi epsilon of x. And so phi epsilon must be a solution. Maybe capital phi is a bad notation. Let's see. Okay, what is a good notation for this? Let's say capital gamma. And so phi epsilon is a fixed point of the equation of this equation. Phi epsilon is gamma phi epsilon. Now you may think that, okay, this looks very complicated. How is it making my life simple? Well, that's because you are thinking in terms of integral operators. Integral operators are nothing but infinite dimensional generalizations of, these are linear operators. They're nothing but infinite dimensional generalizations of matrices. And if you think in that way, you'll see immediately that this is a very, very convenient way of actually trying to compute this object. So let's write these things in terms of a matrix and see what I'm actually doing. So if I have discrete data, sorry, let me just write down what I'm actually about to go. I'm coming to the discrete data part. So a natural guess would be to start with some u1, to start with some phi epsilon 1, to take an iterative sequence. Where you say phi epsilon k plus 1 is equal to gamma of phi epsilon of k, and look for convergence. And if you do this, your natural guess would be that if this limit actually exists, then this limit would be a solution of the fixed point equation. This seems very natural to guess. And this is what does. This is exactly what the Synchron algorithm does. And my point is to show that when you have discrete data, what you're doing is just some matrix multiplications and additions and divisions. It's as simple as that. So let's see what is actually over discrete data. So over discrete data, this is the Synchron algorithm. This is the synchron algorithm. So let's see an example. Suppose you have two data points. Suppose your mu1 is 1/2 delta mass at -1 and 1/2 delta mass at 0. And so not mu1, mu. And your nu is 1/2 delta mass at, let's say, 0 and 1/2 delta mass at +1. Now, you start with the following matrix, which is of the form e to the power -1/2 epsilon norm of x minus y squared. This is not a probability matrix. Just start with this. So I have, let's say, -1, 0, 0, +1. And so I compute x minus y norm square. So what do I get? I get in the first term, which is -1 and 0, I get e to the power -1/2 epsilon. Then when I have 0 and 0, I get this is 1. Then when I have +1 and -1, then I get e to the power -2 over epsilon. And then I have +1 and 0, I get e to the power -1/2 epsilon. Right? Now, I want both the marginals to be uniform. Now, in this case, in this particular matrix, the marginals, none of the marginals are uniform. In fact, this is not a probability matrix. So in my first step, what I'm going to do is make column sums uniform. One half, one half. How will I do this? Well, I look at all the column sums. The column sums are over here. So 1 plus e to the power -1/2 epsilon. Over here, so e to the power -1/2 epsilon plus e to the power -2 over epsilon. I will divide by the column sum and multiply by half. And so what I will get the matrix as is e to the power -1/2 epsilon. I will multiply by half and divide by 1 plus e to the power -1/2 epsilon. Same thing here, 1/2 divided by 1 plus e to the power -1/2 epsilon. Over here, this would be e to the power -2 epsilon. One half divided by e to the power -1/2 epsilon plus e to the power -2 epsilon, and so on. Same thing here. So what I have done now is that I have gotten 1/2 and 1/2 as my column sums. And my row sums are something else, but they're not 1/2 of the 1/2. In the next step, I will make the row sums 1/2, 1/2. What I will do here is that I will add by this row sum here, R1, R2. So I will divide by the row sums and I multiply by half. You understand what is going on here? So in the next step, I would get a matrix where I would take this entry, the 1/1th term here. Then take this 1/1th term here, divide by the row sum, multiply by 1/2. Over in this matrix, I will take this 1/2th term here, same thing, take the 1/2th term here, divide by the row sum, R1, multiply by half, and so on. And now the row sum is 1/2, 1/2. But now the column sums have now changed. And so I will change it to, again, make column sums 1/2, 1/2. And then I go on repeating this.
You have these terms that are in the denominator of the denominator of the denominator that go back and depend on the original.
I'm sorry?
The normalization factors get nested, like the denominator.
That is exactly what is happening
R1 and
here.
so on. Yeah.
Which is exactly this term. if you notice it, this is exactly the term that I'm doing here. And that's my next point here, is that what you're essentially doing is evaluating this particular gamma operator. That's exactly the term. What every time, like look at this R epsilon of something here. Like look at this term over here. So this term over here is basically taking the row sum, because you're multiplying by mu, and this R epsilon is my e to the power minus norm of x minus y squared, which is always there. And you're just adding them up. So that's basically my R epsilon of phi epsilon of mu. And now when you divide by this, you are making nu divided by this. That's when you are making your column sum to be exactly nu. Now in the next step, you sum everything up for the rows, and you get R epsilon of nu over this. And then when you divide by it, you get your row sums to be exactly again mu. And so that's exactly, this is nothing but this iteration in practice. Does this make sense? So what I'm doing for your matrices is nothing but the discrete version of this operator gamma. So if you have to write this down, right over here, my A epsilon and right over here, my A epsilon was the function 0, and my B epsilon was also the function 0. Right? That's why I get exactly e to the power minus norm of y minus x squared. Right over here, what I'm getting is I'm getting that same term, but now my A epsilon and B epsilon, they are the corresponding operators that have been applied to them. Make sense?
Yeah, I don't quite see it with
Okay,
iterative
let's do
sum
this.
versus the
Let's do this.
Brownian motion.
Let's do this.
So
So
is the
at my
Brownian, how does the uniformity connect with the Brownian motion?
the uniformity and Brownian motion has nothing to do with each other. The Brownian motion is coming from the cost function. The uniformity is coming from the marginal constraints. So if you look into this term over here,
So if there was non-uniform marginal constraints, it would be different.
it would be different, exactly.
Okay.
So for example, if I want a constraint to be, let's say, 1/3 here and 2/3 there, then I wouldn't be dividing by half and half. I'll be multiplying by 1/3 and 2/3.
Yeah, got
And
it.
that's because of this term. I'm multiplying by mu. So R epsilon is my exponential term, this exponential term, which is always the same. It always remains the same. And this integral operator is just doing the sum, matrix sums. If you want, I can also write down explicitly what's happening for the matrices.
Yes, I love explicit.
Okay, let's do this.
Verbose.
Okay, let's do this. So at some point, let's suppose your matrix M, K looks like this. The ijth term is e to the power minus 1 over 2 epsilon norm of xi minus yj norm square. And then according to my notation that I've written here, let's say that these are phi epsilon of xi and psi epsilon of yj. So phi epsilon let's say k of xi and psi epsilon k of yj. Good. Suppose this is my matrix at this point, at some point. Now the matrix is chosen in such a way such that the row sum is mu, but the column sum is something else. Let's call this to be nu k. Or it could be the other way around. It doesn't really matter. Let's see what's the first step that I'm doing. Yeah, okay, so this is the correct way of writing this. Let's say this is nu k. Now my first step would be turn column sums to nu. So how will I do this? In my new matrix, I would call this to be mk prime. My ijth term, the ijth term would be the original ijth term which is e to the power minus 1 over 2 epsilon, norm of xi minus yj is norm square, phi epsilon k xi, psi epsilon k yj. I would divide by nu k at what entry? This is for the, okay, so I have clearly, the row sum should be mu and the column sum should be nu k. Nu k, and this is mu. So nu k of g, so yg, is I would divide by, and I would multiply by nu of yg. Good. This has turned my column sums to be nu and row sums to be something else, mu prime. Is this clear?
Yeah.
Very good. Now let's expand what is nu k. Now, because nu k's are my column sums, what is my nu k of g? So nu k of g, or yg, this is the sum over all I, e to the power minus 1 over 2 epsilon, xi minus yj, norm square, phi k, so phi epsilon of k, xi, and sorry, I also have to multiply. Yes, okay. So I should really write this one, I should really write this as mu of xi times nu of yj as well. That's how my potentials are defined. And so then this is mu of xi, nu of yj, mu of xi, mu of yj. And so this would be mu of xi. And so these are all these terms here. And then I'll pull out all the yj's terms, which is just nu of yj. Now, if you look into this term here, what do you see? What you see over here is that this is nothing but a discrete version of the Brownian operator R epsilon applied to the function phi epsilon k times mu. Okay, you have to normalize it by 1 over n, you have to multiply by the constants, but that's exactly what's happening. And that's the term that you see here. That's this term that you see here, over here. And so this new term, which is sitting here, which is nu of yj over nu k of yj, that's my term, nu k of yj. That's my term, which is nu divided by r epsilon, phi epsilon k mu, applied to yj. That's this term here. That's this term here. And now the next time you do the iteration, where you make the row sum to be mu, you would do exactly the same thing. You take r epsilon of this term, and then you take 1 over this to get this mu. Make sense?
Yeah.
Okay, so that's why this is a discrete version
Thank
of
you.
that same of this operator.
I have a question.
Yes, go ahead.
How quickly does this converge in practice?
Very good question. So that's actually one of the main research questions. How quickly does it actually converge in practice? Well, let me talk about this a bit more. So, so this matrix iteration is what is called the synchron algorithm. Iteration is called the synchron algorithm. And the million-dollar question is how fast does it converge? We'll talk much more about this next time, but let me give a brief overview of this. How fast does it converge? So the matrix algorithm itself, under nice conditions, where the cost functions, the ratios of everything is bounded above and below very nicely by constants, is known to converge exponentially fast. Okay, this is the original proof of Synchron. There's a very beautiful proof which uses very nice projective geometry to prove this thing. So under nice conditions, this matrix algorithm, under nice conditions, by which I mean, so so everything is separated. All ratios bounded above and below. So all the pairwise cost, for example, they have to be all bounded above and below. So then this is known to converge exponentially fast. Converges exponentially fast. And so when you actually apply it to discrete data, this is not a problem because it converges exponentially fast. The problem arises is that when you have a large number of data, because in continua, when you have densities, then all these ratios, they get closer and closer to each other. So you can't really have like well-separated data. And it is known that IPFP for densities can converge very, very slowly, if at all. However, on densities, it can be very slow, if at all. I mean, it does converge. We can actually show by just very soft arguments that it will converge under very minimal assumptions, but it can be very, very slow to converge. Certainly not exponentially in all cases. So, so going back to your question, yes, it converges exponentially fast, but that exponential rate can become very bad as the data size grows. Okay. Does it answer the question for now? I'll talk more about this. A large part of modern research is about the speed of this convergence when you make assumptions on the densities. Okay, but we don't actually fully understand. I mean, of course, there's also the other parameter epsilon that's involved that also makes this convergence difficult. And so what you would really like to understand is whether there is exponential convergence for all small enough epsilon under nice assumptions on the marginal densities. And that question is still quite open. We have some answers, but they are highly restrictive.
Does any work look at how slightly modifying the marginals so that you get fast convergence? Like relaxing the marginals somehow in a ball or something?
So the only one that I know is that what people do is that they take a marginal and they add some heat flow to it. So they add some Brownian noise, or in other words, they convolute it with some Gaussian transition, and that makes the marginals much smoother. And
this
then
is
they
like
try
Justin
to show.
Solomon's stuff on this?
Many other people do this, like the statisticians also do this. Some PD people also use it. Yeah, many people do this. We have some understanding of it, but still, that doesn't really help. The main difficulty of it is that you really want to use this for small values of epsilon. So you really want to have a bound of convergence which is uniform over all small epsilons. And that seems very hard. And I'll talk about this in the next class. Why is it hard is because there's a certain geometry which is playing a role here, and the geometry has singularities. But we'll talk about this next time. Okay. But yeah. But the proof of the matrix convergence, you can easily find it online. It's linear algebraic proof. You have to construct a matrix. So you have to construct a metric for which this iteration phi becomes a contraction. And then this gamma, this iteration actually becomes a contraction. And once you find this contraction, then you can show this exponential convergence. But this doesn't really work so well in continuum. Are you guys all right? Any other questions? But this is exactly the current research problem. All right, okay. So moving on. So let's go back to, so this is the iteration that I'm trying to solve here. This is my iteration that I'm trying to solve here. And so moving on, let's try to argue, give an idea of Forte's proof to show that this iteration actually converges, and how to show that there exists A epsilon and B epsilon such that the Schrödinger bridge actually exists. So an idea of Forte's proof of convergence. Of convergence and the existence of the Schrödinger bridge, leading to existence of Schrödinger bridge. Good. So let me see here, 1 second. Okay. All right, okay. So yeah, so this is the idea that we had is e to the power minus A epsilon. 1 second here. Right, so, okay, so let's look into this. Phi epsilon is 1 over R epsilon of the epsilon. So let me just write this down, this iteration again. So what is gamma phi? So going back to the fixed point equation. So I want, this is my phi epsilon is equal to gamma of phi epsilon, where gamma of any function, let's say u, this is 1 over R epsilon. Okay, 1 second. So 1 over R epsilon, nu over R epsilon, phi epsilon times mu. Mu over R epsilon, phi epsilon, so some u times mu. Right. I hope I translated it correctly. Let me just check once again. So A epsilon over epsilon, e to the power minus of this is 1 over R epsilon. So that's phi epsilon. And so that becomes, yeah, exactly. Okay, good. So one thing that you would notice from this iteration, so the first observation is that I'm going to iterate, right? So I'm going to do an iteration where iterate where I'm going to do uk plus 1 is equal to gamma of uk. That's my iteration. So my first observation is that if u2, which is gamma of u1, is a function that is pointwise smaller than u1, then u3 is less than or equal to u2. And in fact, uk plus 1 must be less than or equal to uk, i.e., the sequence is decreasing. It's my first observation. All right, okay, why is this? So what I'm going to use here is the fact that R epsilon is my conditional expectation operator. So remember, R epsilon has this property that if a function is non-negative, R epsilon of that function is always non-negative. In fact, it's monotone. If two functions, one is smaller than the other, then R epsilons must be smaller than the other. So let's start with U2 is less than or equal to U1. So why? So suppose U2 is less than or equal to U1. This implies that R epsilon of U2 mu must be less than or equal to R epsilon of U1 mu. Because mu is non-negative, multiplied by both sides. So this has to be non-negative, by the way. I'm assuming everything is non-negative. It's not important for this argument, but just all the functions are non-negative. This must be true. But that would mean that if I look into nu over R epsilon U2 mu, this must be greater than or equal to nu over R epsilon U1 mu. But this would mean that R epsilon of nu over R epsilon U2 mu must be greater than or equal to R epsilon nu over R epsilon U1 mu. But then this would mean that 1 over R epsilon of nu over R epsilon must be less than or equal to, so this is my U3. This must be U2, which is 1 over R epsilon, blah, blah, and so on. So if U2 is less than or equal to U1, using the monotone property of conditional expectation operator, I get U3 must be also smaller than U2. Does this make sense? And therefore, by iteration, by iterating, I get U1 is greater than or equal to U2, is greater than or equal to, and so on. This becomes a decreasing sequence. All decreasing sequences must admit limits. Therefore, U infinity, which is the limit of UK, must exist. In fact, I'm assuming everything is non-negative, so I'm going to assume that everything is non-negative. So it also follows that every UK is also non-negative. So if U1 is non-negative, every U2 is non-negative. Why? Because again, same deal. R epsilon, look at U2, R epsilon of U1 times mu is non-negative. Nu over that is non-negative. R epsilon of non-negative quantity is non-negative. 1 over that is non-negative. So this is always non-negative. So they're always bounded by below. And I have this mu infinity, which is the limit of UK. This will exist, and this should be non-negative. Good. So just by monotonicity, I can say that this limit actually exists. But there is a problem with this argument. The problem with this argument is that this limit could be actually 0. And this is because this function is positively homogeneous in U. This limit can be actually 0. And one has to do a slightly careful, a very slight modification to this argument to show that this limit is actually not 0. I'll leave it to this modification, what this is, but there is a very slight modification you need to do to this argument to show that the limit is not infinity or 0. It doesn't blow up. I mean, it doesn't blow up because it's bounded above by U1. It's really non-negative. The bigger problem on this argument is how do I even guarantee this statement? How do I start my iteration? Good. So what am I saying here? If I can pick U1 such that in my first step of the iteration, U2 is less than or equal to U1, then it's kind of almost immediate that the sequence converges and the limit exists. If the limit exists, it's not very hard to see the limit will satisfy the fixed point equation, but I'm coming to that. Good. So the question is, how do I pick a U1 that will satisfy this constraint? So observation 2, you're following this argument so far? It is difficult to find U1 such that U2 is less than or equal to U1. And so this is where Forty's argument becomes clever, is that it modifies the scheme. So modify the iterative scheme to the following. So what is this modification that we're doing here? 1 second. So the modification that we will do is that we are going to look at UK plus 1. So modify scheme 2, pick any U1, and then define UK plus 1 to be the minimum of the two, which is phi of UK and the minimum of U1. Okay, so you pick U1 and you apply this problem that is phi of UK to U1. All right, okay. How does this help? Still monotonicity. So here what I have done is that I have forced my U2 to be less than or equal to U1, right? Because just by definition, U2 is the minimum of phi of U2, U1, and U1, so it's smaller than this. And again, the same conditional operator will work now, because the next time the conditional operator will still keep it smaller than U1, and all the other, now the UKs will be all decreasing, will be now decreasing, and it will converge to some U infinity. Okay, so you can actually show in this case that this will decrease again to infinity.
Why doesn't it get stuck somewhere that's not the solution?
No, it will converge to something. I'm not saying it's whether it's getting stuck or not. We're going to show this doesn't get stuck. It actually gives you a fixed point solution. All I'm saying is that this gives you a decreasing sequence. It always has a limit. That's all.
Okay.
Okay. So this sequence always have a limit, this limit of UK. And the next thing is that this lemma, which we get. So if we pass to the limit, so when you pass to the limit, and you get that U star, or rather U infinity, which is the minimum of phi and U infinity and U1, must be smaller than phi of U infinity. So this is what I get from the fixed point equation. I take the limit, I must get this. The fact that this is less than or equal to this is obvious because this is the minimum of two functions. This is, of course, smaller than phi of U1. The next observation is the following. This is actually an important observation. For any function U, for any U, if I look into phi of u, sorry, I've somehow changed my notation to phi because of my notes. This should all be gamma. I don't know why I'm calling it phi. It's because of my notes, it's written phi. But this is really all gamma. So for any u, gamma of u over u times mu is a probability density. Okay, this might come as a surprise, but I'll tell you why you would expect this to happen. So what I'm saying here, this is of course non-negative. So that is what I'm really claiming here is that if I integrate gamma u of x over u of x times mu of x dx, I would get exactly 1. Now, why is this happening? You can prove it by direct algebra, but this is really a consequence of the synchron algorithm or the algorithm which is running in the background. You have to verify that when you do this matrix algorithm, and so in the matrix algorithm, if you start, okay, maybe I should go from here. So why is this true? If you start with a matrix, so if you start with a matrix, or rather in continuum matrix, which has u here, is as your this row sums, and then you do a step which is you go into make the column sums new, then you get something over here which is new. The column sums has become new, and now I'm again flipping my rows and columns.
Can you remind me, if you say column sum, are you saying take each column and sum it up, or sum the row by summing over columns?
A column sums means that you take every column and you just add up all the elements. A row sum is you take every row and you add up all the elements. That's a row sum. A column sum is take every column and add up all the elements. 1, 2, 3, 4. The row sums are given by R1 equals to 4, R2 equals to 6. Column sum is given by C1 is equal to 3, C2 is equal to 7.
Great.
So if you have a joint density, gamma xy, then a row sum corresponds to you fix a row which is x and you integrate over y. That's my row sum, R of x. And my column sum, C of y, would be integrate gamma xy, and you integrate over dx. That's my column sum. So row sums and column sums are just taking the marginals. Okay, so what was I saying is that, okay, so if you take a joint density, which is you can represent this by a matrix, and you do one iteration of synchron algorithm, you get another one where now the row sum, so this suppose the row sum was mu, and now the row sum is not mu. It's something else. Row sum is not mu. And you can ask, what is it now become? Well, it's exactly this guy. This has become this gamma of u over u times mu, where u is whatever the entry was at this point. Okay, so this would be like e to the power minus 1 over something, and then this would be u of x. So this is a calculation that you have to do to check that this must be true. By definition, for any u, gamma u over u times mu, this is always, the integral is always 1. Now, once you have this observation, and once you have this property, u infinity is less than or equal to gamma infinity, And now it actually immediately follows that u infinity must be also equal to gamma infinity. Why? So now my final observation is that u infinity is less than or equal to gamma of u infinity. However, if I integrate my gamma of u infinity over u infinity, mu of x dx, I should get 1. But this ratio over here is greater than or equal to 1. But this would mean that mu almost surely u infinity of x is actually equal to gamma of u infinity of x. And therefore, I have solved. Thus, u infinity solves the fixed point equation. Okay. So again, let's go over the argument here. How does the argument work? I want to solve the Schrodinger system of equations. So the Schrodinger system of equations is given by a solution of a fixed point equation, which is written here. This is my fixed point equation. It's actually how I get this fixed point equation is that I combine two equations of Schrodinger systems from the two marginal constraints, and I combine and write one equation. That's my Schrodinger system. That's my start. I want to prove that this actually has a solution. And the way I do this is that I construct an iterative scheme and I investigate whether this iterative scheme admits a limit. So how does it do this? How do I do this? You can show this iterative scheme by a matrix algorithm. This is a Synchron algorithm. Or you can continue to write it in terms of the integral operator. In that case, it just becomes the IPFP algorithm. And idea of Forte was that you observe that if you find that U2 is less than or equal to U1, then it automatically follows that the sequence is decreasing because the gamma operator is monotone and it keeps on, the sequence is decreasing. Every decreasing sequence must have a limit. By continuity, such a limit must satisfy the fixed point equation. This is all clear. The main problem is that how do I find U1 that will always see that U2 is always less than or equal to U1? And this is not usually true. So what Forte does is that he just forces it. He says, okay, you modify the iterative scheme to pick some U1 and define UK plus 1 to be gamma of UK minimum of U1. Once you do it, now you get a decreasing sequence. And of course, the price that you pay over here that you limit satisfy this equality, U infinity is equal to the minimum of gamma U infinity and U1, not the first one, but this modified one. But this is enough. Because U infinity from here we get must be less than or equal to gamma of U infinity, because that's just because it's the minimum of these two functions. And now you make algebraic observation, you can just directly plug in your formula and verify this, that for any U, gamma U over U times mu is a probability density that you can integrate and it gives you exactly 1. Our way to see this is that this is the density that appears in the Synchron algorithm, but you can just directly write down the algebraic notation and solve for it. But once you do this, it now follows that U infinity, for which U infinity is less than or equal to gamma of U infinity, will also satisfy that this is a probability density. But the ratio that I'm integrating is greater than or equal to 1 by this property. And therefore, mu almost surely it must be equal to 1.
But isn't that what's special about infinity? Isn't everything true for any k? Isn't that inequality true for any k because it's just the minimum at that k? What's special about infinity?
Well, that's because it is true for any k, but then once you go here, you get that then U infinity is equal to gamma of U infinity, which is not going to be true for any k.
Okay, right there. Okay, great.
Okay. And so it satisfies the fixed point equation, and therefore you are done. Good. And so this is a beautiful argument of Forte, which uses Synchron algorithm to show that the Schrodinger system of equations actually has a solution, and now we know that the Schrodinger bridge actually exists. Okay, so we will stop here We'll continue with the study of synchron algorithm next time. We'll also talk about two things that I thought I would do today, but I will do it next time. So the first thing that we will do is that we'll talk about duality, which is also something very important for this entropy regularized optimal transport. There's a dual formula and a modified Benamo-Brenier description. So once we have these two things done next time, then we'll talk about the geometric theory of synchron algorithms, which these are all really cutting edge of current research to understand the convergence rates of this algorithm. Okay, good. I'll stop here. If you guys have any questions, please ask me now.
Question.
Yeah, go ahead.
So if we wanted to compute this entropic distance, let's say between two continuous measures, like numerically, we would need to choose a discrete approximation of the two measures.
Right.
How is that done? What is the appropriate way to discretize
So
two
again,
measures?
okay. So the natural way to do this is that you take IID samples. Whether this is the best way or not, I don't know. But certainly for the case of IID samples, this has been well studied. And now something is wrong here. Yeah. So you should go back and check this textbook by Chewy, Nilsved, and Rigole. They give a whole statistical theory of what happens when you want to statistically estimate this from data, from IID data. So two things here. In general, people's interests are not to estimate the entropy regularized problem. They are really interested in estimating the optimal transport solution. They do the entropy regularized one because you can solve it by the synchron algorithm. So there are two steps of errors. One is how much is EOT different from OT, depending as a function of epsilon. And the other is how much is my estimation error of EOT, that is depending on the number of samples that I take. So the first part is the one that we will focus on because that's more mathematical. That's the error, what happens as you take epsilon going to 0, what is the error that you're making. The second part is what is called statistical complexity. And again, this you have to, if you make nice assumptions on the densities, for every positive epsilon, you can show that this you can do it efficiently in parametric rate, which is n to the power minus 1/2. So if you want to estimate directly optimal transport from statistical data, there is a curse of dimensionality. You can show that you take something like n to the power, the rate of convergence is n to the power -1/d, where d is a dimension. So if your data is coming from 50-dimensional problem, you essentially have no power. You just cannot do this. The space is too large. But we can show that for every positive epsilon, you can estimate the entropy regularized problem in n to the power minus 1/2, which is the parametric rate, assuming that the densities are nice and sub-Gaussian densities are enough. So that's one. And the other part is that how good are you as epsilon goes to 0? So that's the other part.
Okay, so this, yes, I've seen this curse of dimensionality, this n to the -1/d. That's the convergence rate of the Wasserstein distance between basically a random, like this empirical measure and the measure
That's
that
right. You cannot beat n to the power 1/d. This is absolutely there is no way to make this better.
Okay.
I don't know of any work which says that, okay, if instead of random data, is there a way to have like deterministic discretization, which will give you better convergence of entropy regularized optimal transport? I don't know of any such work, but it could be possible.
Okay,
it might be possible
if you were to deterministically discretize. Okay, yeah.
Yeah, if you can partition the space in some nice deterministic way, which will be a better estimate of the entropy regularized problem, I don't know. This will be completely open.
Okay, yeah, that's a good question, though, I feel like.
That's a good question, exactly. Even do it for R1, do it for the circle. Do it for the unit interval.
Okay, so intuitively it'd be, but I mean, like, as you take a larger and larger random sample, that's going to approach some sort of optimized deterministic.
Yes and no. When the space gets large, take the dimension to be large, random samples are actually become very different from, let's say, a grid point. A grid point is much more regular. So in high dimensions, you can see like grid points are still very regular. But if you do random sequences, they tend to cluster. They will cluster in certain areas of space because there's just too much space. So maybe in one dimension, yes, it's more regular, but in high dimensions, it's not even in one dimension, you can actually come up with systems. It's like, for example, what are called these determinantal systems, which are much more regular than random systems. Random systems are actually not that regular, and this certainly fails in high dimensions.
Sorry, so I guess what we're saying is if the deterministic would just be like a projection onto like the finite dimensional, like basically finite dimensional combinations of Dirac masses, right? If we project onto that subspace, that would be the deterministic
Right,
approach.
exactly. So there are many ways that you can find a sequence of finite points such that the uniform distribution on that sequence of finite points approaches your density in whatever way that you want. You can try to construct those. So you can ask the question that if I'm trying to estimate my entropy regularized optimal transport, is there a way I can deterministically divide space such that I get good rates of convergence? I don't know the answer to this.
Okay.
So random IID data is certainly not that regular. Okay, so I think Emma has a question. Emma is asking, why does taking the minimum not change the induction for showing that the sequence is decreasing? Can you elaborate why your U2 is this? Okay, so let's go back to this point here. So I have this U2. Sorry, so what did I get here? Okay, so I'm going to take this U2. So U2 is less than or equal to U1 is just by definition, because I take gamma of U1 and I take minimum of U1. So U2 is less than or equal to U1. Now let's take U3. When I take U3, U3 is gamma of U2 minimum U1. But everything is monotone. Gamma is monotone, minimum is monotone. So gamma of U2 minimum U1 is less than or equal to gamma of U1 minimum U1, but that's just U2. So everything is monotone, and that's what I'm using here. Does this answer your question, Emma? Emma, are you there?
Yeah.
Right. So if
U1 doesn't decrease on the first step to U2, then you're just stuck at U1 the whole time.
Correct. And
Why
that case,
isn't that an
U1 is my
issue?
solution. And that case, U1 is just a
Okay.
solution. If U1
Okay.
U2 doesn't decrease, then U1 is my fixed point equation. That's what I've proved here.
Oh, okay.
In fact, that's exactly what I'm getting from here. Look at what I'm getting here. The observation is U infinity is less than or equal to gamma of U infinity. What does that mean? That when I apply gamma again, my next step doesn't decrease at all. I'm stuck here.
So does that mean that if I apply gamma once and it's bigger, then I know that U1 already satisfies the
Exactly.
fixed point?
You're
Okay.
already at the fixed point.
I
Otherwise,
understand.
it will
Thank you.
somewhere or the other, it will decrease. That's exactly correct.
Okay.
Any other questions? All right. Okay. So if not, I'll see you guys again on Wednesday.
Excuse me, can I just clarify what you said in response to
Yes,
my
please.
question? Sorry, so like I guess I just don't understand. In higher dimensional space, if you were to take a random sample of some Gaussian, let's say in some higher dimensional space, if you took a large enough sample size, wouldn't this be essentially a projection? Like, wouldn't this approach something that's like as close as possible for a finite size? Basically, like the closest possible measure, discrete, finite sum of delta masses, which
No,
approximates the.
there is no such thing called projections there, but it's certainly not going to be that. The fundamental behavior of randomness would be that there will be some places where your data will cluster too much. There'll be some places where your data will spread out too much. And at those places, it's not going to be a good approximation of the Gaussian. Why Gaussian? Just take uniform over a cube and you can try to see this. This is not going to happen. Your random data is not going to be your best discretization in whatever way you want to measure it. By the very nature of randomness, things will become quite, I mean, how should I say it, like clustered.
Right. I agree with that, but it just seems like for a large enough sample size, it would approach something very close to the deterministic optimal
Of course, for a
discretization.
large number of samples, it will approach this, but the question is, how large do you want it to be? And that's where the problem is, right? That's where I was saying that if your rate of convergence is n to the power minus 1 over d, and if d is 50, then you want your n to the power minus 1 over 50 to be very small, and that requires a gigantic number of sample sites.
Okay, yeah.
So of course, with large number of samples, it will happen. But how large is large? Like a trillion to the power trillion is very large, but that's not feasible.
Yeah, okay. That makes a lot of sense. Okay. Thank you.
Okay. All right, okay. See you guys next time.